turn over to page 64, please. On page 64, we have the review questions because you have your second test to take. You're supposed to define these terms, and he will have 5 words from here that you will define, okay? So remember, pure substance, they all have the same properties throughout, whereas a mixture is a combination of more than one pure substance, or I should say 2 or more. Remember that the homogeneous mixture is just where, no matter where you take the sample, it's the same. If it's heterogeneous, where you take the sample, it'll be different. The law of conservation of mass, something about when there's chemical or physical processes, you'll start and end with the same mass. That's all. You know, unless you're doing a nuclear explosion, you should start and end with the same mass. And you can say that. I would count that as correct. Element, you can't be broken down chemically into simpler substances. Compound, composed of 2 or more. You can define it just like you would a molecule, composed of 2 or more elements. Or you could even say 2 or more atoms, and I would take it. Okay? H, the law of definite proportions. You need to tell them that, you know, there's a specific recipe for any molecule. You could say that. Specific recipe or ratio for any molecule. Molecule, 2 or more atoms combined together. That's a compound, isn't it? Law of multiple proportions. O. Ouch, ouch, ouch. I will tell you, you do not have to define it on your test. Be able to use it. Do not waste your brain memorizing it. Okay? Be able to use it like we did up here, where you're holding one, the other one will be in a small whole number ratio to one another, remember? Okay, all right. And then isotopes, they're just atoms within an element with differing numbers of neutrons. Okay, go to 2. Classify the following as an element, compound, heterogeneous mixture, or homogeneous mixture. Now you guys are going to tell me on this one. We have a bowl of fruit covered with yogurt. Which one is that? Hetero, good, heterogeneous mixture. How about a sample of helium gas, which cannot be broken down into simpler substances? That's an element. If it can't be broken down further, it's an element. Now let me tell you this right now. If it's an element, if it can't be broken down further and it's made up of all one kind of atom, you're going to say element. If it's made up of all one kind of molecule, you're going to say compound. Okay? That's how this works. All right, so on C, a sample of sugar thoroughly dissolved in water. What is that? Homogeneous mixture, good. D, a sample of sodium bicarbonate, which is baking soda, and he tells you it can be broken down. What is that? That's a compound. When you've got a molecule, it's a compound. E, several grams of magnesium, which is one of the simplest. Okay, so what is that? Element. That's an element, good. F, magnesium oxide. That's a compound. You hear 2 things there, right? Magnesium and oxygen, oxide. Strawberry. Heterogeneous, even in the smoothies. Okay. It's like Tim Hawkins. Come back to a previous one, right? All right. And then H, a cup of tea with no leaves in it. Homogeneous, very good. Think homogeneous milk, you could say homogeneous, it's okay, it's all good. Homogeneous. All right, number 3. A student does a chemical reaction with 2 chemicals. The total mass of the 2 chemicals is 45 grams. When she is done, she finds that the mass of all the chemicals she has collected is now only 34.5 grams. Has she collected all the products of the reaction? No, it has to start and end with the same number mass-wise, doesn't it? And so, that's why, because she has to start and end with the same mass, and she doesn't. She's lost something, probably in a gas, right? Number 4, unless it just crept away, you know, and she wasn't looking. That would be living things. No. Okay, number 4, in the situation discussed in problem 3, what is the mass of the chemical or chemicals the student didn't collect? Well, basically, all you're doing there is you add up how much well, it tells you the total mass of the chemicals was 45 grams, and then it tells you that she now has 34.5 grams, and so you just subtract the 2 and you get 10.5 grams, and that's what she didn't collect, right? Okay, number 5, water is a compound that can be broken down into hydrogen gas and oxygen gas. However, a mixture of hydrogen and oxygen gas looks and behaves nothing like water. Why? It's a new, remember, I probably read it wrong. Every molecule has new characteristic properties. However, a mixture of hydrogen and oxygen gas looks and behaves nothing like water. Water is a compound. Oh, yeah. Okay. It's because when you have a molecule, it has brand new characteristic properties. Is that worded weirdly? Or,
yeah.
Thank you, okay. Or it's just me and I'm having an ADD moment. Okay, I'm sorry. I'm not trying to pick on anybody with ADD here. Got to do that.
It's all right.
I have those moments for sure. I know, they want me to start calling them senior moments, and I'm like, not until I'm 65, I'm sorry. Got a ways to go, thank you, Jesus. Okay, let's see, number 6, 75-gram sample of white powder is chemically broken down, and it gives us that, what it's broken down to, and an unknown amount of oxygen gas. How much oxygen gas was made? Okay, well, all you gotta do here is you know that you started with 75 grams total, right? 75 grams total. And we know how much of the other stuff is there. We know that we have 29.86 grams of copper, and we have 15.06 grams of sulfur. And so we know if we add those up, that's going to tell us how much oxygen is left. And actually, I did it here. So if you add these up, you get 44.92 grams total. And if you subtract that from this, let's go ahead and do it. Oh, it's too ugly. 75.0 grams minus 44.92 grams. Remember, you've got to go to that place. And so you're going to end up, what comes out of your calculator is this. But you've got to lose this. So you're going to go 30.1 grams of oxygen. Okay? Everybody sees why? Because this only goes to the 10th place, so this answer has to go to the 10th place. You take the least precise. Okay. So that's the answer for A. B, suppose you want to make 11 grams of white powder with no leftovers. How much copper, sulfur, and oxygen will you use? Okay, so if we wanted to make 11.2 grams, we would go ahead and do the batch we want to make divided by the recipe batch, and that would give us the number to multiply the different things by. We have 3 significant figures here. We would take this number and multiply this by that, and that gives us the oxygen. Do I have to do that, or can you guys, you see how to go from there? Then you just multiply the ingredients, and that tells you how to get there, right? Watch your significant figures. Let's go on. Okay, 7. On number 7, a chemist makes 86-gram block of black powder by reacting that with that. If a student breaks down 144 grams of powder, what mass of magnesium and what will the mass of oxygen be? Well, here you've got this one is the new group divided by this one, which was the old group, right? And that's going to give you 1.667. So if you take the original mass of manganese and multiply it by that, it will give you the mass you need. And if you take the original amount of oxygen and multiply it by that, it will give you the amount of oxygen you need to come up with the new batch. We okay on those? We're okay on Toll House cookie batch increases? Okay, that's what we're doing. Toll House cookies, yes. Everybody's going to go home and make Toll House cookies. Number 8, in an experiment, chemists react 7.85 grams of manganese with 22.29 grams of oxygen to make that much powder. Is it the same as the powder made in problem number 7? Okay, so we go back to number 7. Oh, and we had those amounts. So in this case, you would take the manganese, which the given amount was this, divided by the one that you came up with by multiplying it by 1.667, which would be this. And so if you do that, that's going to give you 1.717. And then if you do the same with the oxygen, which would be 32 divided by 53.34, it gives you a different number. So it's not the same. Did you get not the same? Okay. So it's not the same. You could have flipped this, couldn't you? You could flip those. Don't think you can only do that one way. You're just seeing if the ratio is the same. Okay. Number 9. In another experiment, a chemist reacts 10 grams of manganese with 5.8. Oh, no, that was the one we just did. Number 10, write down the original propositions. You have to do that. Note what's wrong with them. That's number 11. We already talked about that. Number 12, a chemist makes 2 different compounds with the same 2 elements, tin and chlorine. He reacts 50 grams of tin with that much chlorine. There's no leftovers. He then reacts 50 grams of tin with that much chlorine. Once again, there's no leftovers. As the first compound has 2 atoms of chlorine in the molecule, how many atoms of chlorine are in the second compound? Now, I don't know about you, but I knew that there was 1 molecule of chlorine in the first one, right? Leftovers, see that reacts with that. Once again, if the first one has 2 atoms of chlorine in the molecule, I just took how much mass he had and divided it by 2. That told me how much 1 atom of chlorine. He gave this and said this is 2 molecules of chlorine, right? So I divided that by 2, and that gives me 14.94 grams for 1 molecule. And then he says the last one has 4, so I just multiplied that by 4. Now that's how I did it. Did anybody else do it that way? Okay, the way he did it was he took the amount of mass, the 59.74 grams, oh well that's, I continue, divided by, and that gives me 3.999, which is 4. The other way you can do it is you could actually do this divided by the 29.87. And that gives you 2, but you know that you started with 2, so then you go to 4. Personally, I think it was easier to just find out what 1 molecule weighed and multiply it by 4. That, to me, was the most straightforward way to get the answer. Okay, we already did 13. 14. What three particles make up most atoms? Proton, neutron, electron. Which one is positive? Proton. Which one neutrally charged? Neutron. Which one the negative charge? Electron. You need to know that. Describe the plum pudding model and indicate what experiment demonstrated it wasn't correct. So you can say the raisin bread model where the bread is the positive charges and the raisins are the negative charges, right? And then you'll talk about the foil, you know, the positive charges hitting the gold foil and it's scattering in an interesting way. Describe the planetary model of the atom and indicate who proposed it. That would be with the positive charges in the center and the electrons going around the outside edge, and that was Rutherford. Of the 3 particles that make up most atoms, there is 1 particle that doesn't appear in some hydrogen atoms. Which is that? Neutrons. Neutrons. Which of the following are isotopes? What are you going to look for? Okay, because you're looking for who has the same number of protons, and that would be A and C. And then it says, which of the 2 isotopes in that problem would be the heaviest?
A. They're both the same?
No, they're not. Look at the number of neutrons. Look, be careful. They listed them differently.
Okay.
So A would be heavier because it has more neutrons. Which, okay, we did that. When you burn a fuel, what besides fuel gets used up?
Oxygen.
Oxygen. And what particles do you find in the nucleus of an atom?
Protons and neutrons.
Okay, you guys all right? You're going to take this test. Hey, if you haven't done this already, before you come to class next week, hold still for just a minute. Before you come to class next week, make a copy of the first 2 pages inside your book. Both. See how I got both? That's what you want in a sheet protector. You're going to need it for the rest of class, okay? Have a good week.